Welcome to today's comprehensive training on defending artificial intelligence systems using the Mitre Atlas framework. I'm excited to share with you how we can better understand and protect against the evolving threat landscape targeting AI systems. Think about this for a moment. Artificial intelligence has become the backbone of countless critical systems in our organizations. From fraud detection algorithms protecting our financial transactions to computer vision systems securing our physical facilities, AI is everywhere. But here's what keeps me up at night. These powerful systems that we rely on are under constant attack from sophisticated adversaries who understand exactly how to exploit their unique vulnerabilities. Today, we're going to dive deep into the Mitre Atlas framework, which stands for Adversarial Threat Landscape for Artificial Intelligence Systems. This isn't just another security framework. It's our roadmap for understanding, detecting, and defending against attacks specifically designed to compromise AI systems. And trust me, after seeing the real-world attack scenarios we'll discuss today, you'll understand why protecting AI requires a fundamentally different approach than traditional cybersecurity. Let me start by painting a picture of what we're up against. Traditional cyber attacks target operating systems, networks, and applications. But AI attacks? They target the very intelligence of our systems, the models, the training data, the inference processes that make decisions. An attacker doesn't need to break into your network if they can manipulate your AI model to make incorrect decisions that benefit their goals. Real-world attack. Story 1. Microsoft Tay poisoning attack. Let me share the first of many real-world examples we'll explore today. In 2016, Microsoft launched Tay, an AI chatbot designed to learn from conversations with users on social media platforms. Within just 24 hours, the bot had to be taken offline after coordinated attacks poisoned its learning process. Here's what happened. Adversaries flooded Tay with inflammatory and offensive content, knowing that the bot was designed to learn from user interactions. The AI system, without proper content filtering or defensive measures, began repeating and amplifying harmful messages. This wasn't a traditional hack. It was a manipulation of the AI's learning mechanism itself. The countermeasures that could have prevented this attack include implementing robust content filtering, establishing learning rate limits, using human-in-the-loop validation for training data, and deploying sentiment analysis to detect coordinated manipulation attempts. Organizations should also implement real-time monitoring of AI behavior and establish kill switches for rapid response to similar attacks. The reconnaissance phase. Every successful AI attack begins with reconnaissance, and adversaries targeting AI systems are incredibly methodical in their approach. They're not just looking for network vulnerabilities. They're searching for technical papers published by your research team, analyzing your job postings for AI engineers, and scouring academic conferences for presentations by your staff. Think about your organization for a moment. How much technical detail about your AI capabilities is publicly available? Adversaries systematically search open technical databases, including academic journals, preprint repositories like arXiv, and technical blogs. They're looking for information about your model architectures, training methodologies, and even the datasets you use. Real-world attack. Story 2. GPT-2 model replication attack. Here's a fascinating case that demonstrates the power of reconnaissance in AI attacks. Researchers demonstrated how they could replicate OpenAI's GPT-2 model by systematically querying the API and analyzing responses. Using only black box access, they gathered enough information to train a functionally equivalent model. The attack began with systematic reconnaissance of the model's capabilities, input formats, and response patterns. The adversaries crafted thousands of carefully designed prompts to understand the model's architecture, training data characteristics, and behavioral patterns. Through this process, they were able to extract enough information to create their own version of the proprietary model. To counter such attacks, organizations should implement query rate limiting, response obfuscation techniques, behavioral analysis to detect systematic probing, and watermarking of model outputs. Additionally, monitoring for patterns of systematic information gathering and implementing honeypots to detect reconnaissance activities can provide early warning of potential attacks. Real-world attack story 3, Cylance AI antivirus evasion. Cylance's AI-powered antivirus was considered state-of-the-art until researchers demonstrated how to systematically evade it. The attack began with reconnaissance of the AI model's decision-making process through careful analysis of detection patterns. Security researchers reverse-engineered the model's behavior by testing thousands of malware samples and analyzing which features triggered detection. They discovered that the AI system relied heavily on certain file characteristics and string patterns. Armed with this knowledge, they developed techniques to modify malware in ways that preserved functionality while evading detection. The key lesson here is that AI-based security tools can become targets themselves. Countermeasures include implementing ensemble detection methods using multiple AI models, regularly updating model training with new attack samples, using adversarial training to improve robustness, and implementing human-in-the-loop validation for suspicious files that pass initial AI screening. Resource development phase. Once adversaries understand your AI systems, they begin developing the resources needed for their attack. This isn't like traditional malware development. AI attackers need specialized infrastructure, datasets, and models to craft their attacks effectively. One of the most concerning trends I've observed is the acquisition of public AI artifacts. Adversaries systematically collect datasets and models from public repositories, cloud storage, and even victim-owned websites. They're particularly interested in artifacts that represent what you use in production environments. Real-world attack. Story 4, Hugging Face malicious model upload. In 2023, security researchers discovered multiple instances of malicious models uploaded to Hugging Face, one of the most popular AI model repositories. These models appeared legitimate but contained hidden backdoors and malicious code. The attack worked by uploading models that performed their intended tasks correctly during normal operation but contained embedded triggers that activated malicious behavior under specific conditions. Developers downloading these models unknowingly incorporated compromised AI systems into their applications. Organizations can defend against this by implementing mandatory security scanning of all external AI artifacts, using only verified and signed models from trusted sources, establishing internal model repositories with strict validation procedures, and implementing behavioral testing of all models before production deployment. Real-world attack. Story 5, Poison GPT supply chain. Attack researchers demonstrated a sophisticated supply chain attack by creating Poison GPT, a compromised version of a large language model that appeared to function normally but contained subtle manipulations designed to spread misinformation. The attack involved taking a legitimate open source model, fine-tuning it with poison data to embed false information about specific topics, and then distributing it through legitimate channels. The model would provide accurate information about most topics, but consistently spread misinformation about targeted subjects. Countermeasures include implementing comprehensive model validation and testing procedures, using multiple independent sources for model verification, establishing baseline performance metrics for all models, and implementing continuous monitoring for model behavior drift in production environments. Initial access phase. AI systems present unique entry points that traditional security tools often miss. The AI supply chain is vast and complex, involving everything from training data to specialized hardware to model repositories. Each component represents a potential entry vector. Real-world attack story. 6. PyTorch package repository compromise. In late 2022, the PyTorch package repository was compromised when attackers uploaded malicious versions of the popular machine learning framework. The malicious packages were designed to steal sensitive information from AI development environments. The attack exploited the trust that developers place in package repositories. When developers installed what they believed was the legitimate PyTorch package, they unknowingly executed malicious code that could access their training data, model files, and development credentials. Defense strategies include implementing package signature verification, using dependency scanning tools specifically designed for AI frameworks, maintaining isolated development environments, and establishing secure channels for acquiring AI development tools. Organizations should also implement network monitoring to detect unusual data exfiltration from development environments. Real-world attack. Story 7. Shadow Ray. Attack on Ray framework. The Shadow Ray attack targeted Ray, a popular distributed computing framework used for AI workloads. Attackers exploited exposed Ray dashboards to gain unauthorized access to AI training and inference infrastructure. Researchers discovered thousands of exposed Ray instances on the internet, many belonging to major technology companies and research institutions. These exposed systems contain sensitive information, including API keys, database credentials, and access to proprietary AI models and datasets. Organizations can prevent similar attacks by implementing proper network segmentation for AI infrastructure, using authentication and encryption for all AI framework communications, regularly auditing exposed services, and implementing zero-trust network architectures for AI development environments. Model access phase. Here's where AI security becomes fundamentally different from traditional cybersecurity. Adversaries need some level of access to AI models to launch effective attacks. This access can range from simple API queries to full white box access to model internals. Real-world attack. Story 8. Physical facial recognition system. Bypass security researchers demonstrated how to systematically evade facial recognition systems used for physical access control. The attack combined reconnaissance of the AI system with carefully crafted physical countermeasures. The researchers first studied the target facial recognition system by analyzing its responses to various facial features and lighting conditions. They then developed specialized glasses and makeup patterns that could fool the AI while appearing relatively normal to human observers. Defense measures include implementing multimodal biometric systems that don't rely solely on facial recognition, using liveness detection to prevent spoofing attacks, regularly updating facial recognition models with adversarial examples, and implementing human verification for high-security access points. Real-world attack. Story 9. Clearview AI data breach. Clearview AI, a company providing facial recognition services to law enforcement, suffered a significant data breach that exposed their entire client list and search history. This incident highlighted the vulnerabilities in AI service providers and the cascading effects of such breaches. The breach not only compromised sensitive law enforcement data, but also revealed the extensive use of facial recognition technology across various organizations. This raised serious privacy concerns and demonstrated how AI system compromises can have far-reaching societal implications. Countermeasures include implementing data minimization principles for AI systems, using encryption for all stored AI data, establishing strict access controls for AI services, and conducting regular security audits of AI service providers before engagement. Execution phase. When we think about execution in AI systems, we're not just dealing with traditional malware. We're facing adversaries who embed malicious code directly into AI artifacts. Model files, especially those using serialization formats like Pickle, can contain executable code that runs when the model is loaded. Real-world attack story 10. Math GPT prompt. Injection. Attack researchers demonstrated how to achieve arbitrary code execution in Math GPT through carefully crafted prompt injection attacks. The AI system was designed to solve mathematical problems, but could be manipulated to execute unintended code. The attack worked by crafting prompts that appeared to be legitimate mathematical queries, but contained hidden instructions that caused the AI to generate and execute code with access to the underlying system. This demonstrated how AI systems designed for specific tasks can be weaponized for broader malicious purposes. Prevention strategies include implementing strict input validation for all AI prompts, using sandboxing for AI execution environments, establishing clear boundaries between AI processing and system access, and implementing real-time monitoring for unusual AI behavior patterns. Real-world attack. Story 11. Google Collaboratory Resource Abuse. Attackers discovered how to abuse Google Collaboratory, a free AI development platform to conduct large-scale cryptocurrency mining operations. The attack exploited the platform's generous resource allocation for legitimate AI research. The attackers created notebooks that appeared to be legitimate AI research projects but contained hidden mining code. By sharing these notebooks through academic channels and social media, they tricked users into running mining operations on Google's infrastructure. Countermeasures include implementing resource usage, monitoring, and anomaly detection, establishing clear usage policies for AI development platforms, using behavioral analysis to detect non-AI workloads, and implementing time limits and resource quotas for computational tasks. Persistence phase. Adversaries targeting AI systems have developed ingenious methods for maintaining persistent access. Unlike traditional persistence mechanisms that rely on registry entries or scheduled tasks, AI persistence often involves manipulating the core intelligence of the system. Real-world attack story 12. Mobile deep learning model. Backdoors. Researchers demonstrated how to embed persistent backdoors in deep learning models used in mobile applications. These backdoors remain dormant during normal operation, but activated when specific trigger patterns were present in input data. The attack involved training models with poisoned data that associated specific trigger patterns with desired malicious outputs. When deployed in mobile applications, these models appeared to function normally, but could be remotely activated by adversaries who knew the trigger patterns. Defense strategies include implementing comprehensive model validation and testing procedures, using adversarial training to improve model robustness, establishing model provenance tracking throughout the development lifecycle, and implementing behavioral monitoring for deployed models. Real-world attack. Story 13. Web-scale training, dataset poisoning. This sophisticated attack targeted web-scale training datasets by exploiting how data is collected and processed for AI training. Attackers poisoned training data in ways that would only be visible to AI systems, not human reviewers. The attack worked by creating web content that appeared normal to humans, but contained hidden elements that would be processed differently by AI training systems. This allowed attackers to inject malicious content into training datasets without detection during human quality assurance processes. Prevention measures include implementing automated content analysis for training data, using multiple independent validation methods, establishing human-AI hybrid review processes, and implementing provenance tracking for all training data sources. Defense evasion phase. AI-enabled security tools are becoming increasingly common, but adversaries have developed sophisticated techniques for evading these defenses. They craft adversarial examples specifically designed to fool AI-based malware detectors, intrusion detection systems, and fraud prevention tools. Real-world attack. Story 14. Deep learning. Malware detection evasion. Cybersecurity researchers demonstrated how to systematically evade deep learning-based malware detection systems by crafting adversarial examples that preserved malware functionality while evading detection. The attack involved analyzing the decision boundaries of AI-based security tools and then modifying malware samples in ways that pushed them across those boundaries without affecting their malicious capabilities. This showed how AI-based defenses could be systematically defeated by knowledgeable adversaries. Countermeasures include implementing ensemble detection methods that combine multiple AI models, using adversarial training to improve detector robustness, establishing human verification for borderline cases, and implementing multiple layers of defense that don't rely solely on AI detection. Real-world attack. Story 15. AI-based domain. Generation algorithm. Detection. Evasion attackers develop techniques to evade AI-based domain generation algorithm detection systems used to identify botnet command and control infrastructure. The attack demonstrated how adversaries adapt to AI-based security measures. The evasion technique involved studying the features used by AI detectors and then crafting domain names that appeared legitimate to the AI while still serving malicious purposes. This highlighted the ongoing arms race between attackers and AI-based defense systems. Defense strategies include continuously updating detection models with new attack samples, implementing ensemble methods that combine multiple detection approaches, using human analysis for suspicious domains that pass AI screening, and establishing threat intelligence sharing to rapidly respond to new evasion techniques. Collection phase. Adversaries invest significant effort in understanding the AI systems they are targeting and collecting valuable assets. They systematically discover model ontologies, family types, and operational characteristics while gathering AI artifacts and intelligence. Real-world attack. Story. 16. Microsoft Azure AI services disruption. Attackers demonstrated how to disrupt Microsoft Azure's AI services through systematic resource exhaustion attacks. The attack combined reconnaissance of service limits with coordinated denial of service tactics. The attack worked by identifying the computational limits of cloud-based AI services and then launching coordinated requests designed to consume available resources. This prevented legitimate users from accessing the services and demonstrated the vulnerability of shared AI infrastructure. Prevention measures include implementing robust rate limiting and resource quotas, using behavioral analysis to detect coordinated attacks, establishing priority queuing for verified users, and implementing distributed load balancing to handle attack traffic. Real-world attack. Story 17. ChatGPT information extraction. Researchers demonstrated multiple techniques for extracting sensitive information from ChatGPT and similar large language models. These attacks showed how conversational AI systems could be manipulated to leak training data and system information. The attacks involved crafting prompts designed to extract memorized training data, system prompts, and operational parameters. Some techniques used social engineering approaches, while others exploited technical vulnerabilities in how the models processed and responded to inputs. Countermeasures include implementing robust output filtering and content validation, using differential privacy techniques during training, establishing clear boundaries between system information and user responses, and implementing monitoring for attempts to extract system information. Impact phase. This is where adversaries leverage their reconnaissance and collected intelligence to prepare and execute targeted attacks with maximum impact. Real-world attack story. 18. IDME, AI identity verification. Bypass attackers demonstrated how to bypass IDME's AI-powered identity verification system using a combination of deepfake technology and social engineering. This attack showed how AI systems designed to detect fraud could themselves be defeated by AI-generated content. The attack involved creating high-quality deepfake videos and documents that could fool the AI verification system while appearing legitimate to human reviewers. This highlighted the challenges of using AI to verify identity in an era where AI can generate convincing fake identities. Defense strategies include implementing multimodal verification that combines multiple biometric factors using liveness detection and challenge response protocols, establishing human verification for high-risk transactions, and continuously updating detection models with new deepfake samples. Real-world attack. Story 19. Microsoft 365 Copilot insider threat. Security researchers demonstrated how an insider threat could exploit Microsoft 365 Copilot to manipulate financial transactions and business processes. This attack showed how AI assistants could be weaponized by malicious insiders. The attack involved using Copilot's access to organizational data and systems to automatically generate and execute financial transactions that appeared legitimate but were designed to benefit the attacker. The AI assistant's ability to understand context and automate tasks made the attack particularly difficult to detect. Prevention measures include implementing strict access controls for AI assistants, establishing approval workflows for financial transactions initiated by AI, using behavioral analysis to detect unusual AI usage patterns, and implementing segregation of duties that requires human oversight for critical operations. Real-world attack. Story 20. Large language model infrastructure compromise. Researchers discovered a sophisticated attack campaign that compromised large language model infrastructure to steal computational resources and sensitive data. The attack demonstrated how valuable AI resources have become to cybercriminals. The attack involved compromising cloud-based AI training and inference infrastructure to steal GPU resources for cryptocurrency mining and to access proprietary models and datasets. The attackers used these resources to train their own models and sell access to stolen AI capabilities. Countermeasures include implementing comprehensive monitoring of AI resource usage, using authentication and encryption for all AI infrastructure communications, establishing anomaly detection for unusual computational patterns, and implementing network segmentation to limit the impact of compromised systems. Comprehensive countermeasures. Now, let me share with you the comprehensive countermeasures that every organization should implement to defend against these real-world attack scenarios. These aren't just theoretical recommendations. They're practical defense strategies based on lessons learned from actual attacks. First and foremost, you need to maintain a complete inventory of all AI assets, including models, datasets, training pipelines, inference APIs, and supporting infrastructure. Classify each asset based on its criticality and potential impact if compromised. Implement continuous monitoring of access patterns, performance metrics, and behavioral baselines. This visibility is essential for detecting anomalous activities that might indicate an attack in progress. Next, implement rigorous verification procedures for all external AI artifacts, including models, datasets, libraries, and frameworks. Use cryptographic checksums, digital signatures, and behavioral validation to ensure integrity. Establish secure channels for acquiring AI components and maintain detailed provenance records. Consider implementing air-gapped environments for critical AI development activities. You must implement zero-trust principles specifically adapted for AI environments. This includes authenticating and authorizing every access request to AI resources, encrypting all data in transit and at rest, and implementing microsegmentation for AI infrastructure. Never trust any component by default, including internal AI systems and development tools. Deploy specialized detection systems that can identify AI-specific attack patterns, including adversarial inputs, model extraction attempts, and data poisoning activities. Use behavioral analysis, statistical anomaly detection, and machine learning-based threat detection specifically designed for AI environments. Continuously monitor model performance against established baselines using automated testing procedures that can detect model manipulation, backdoors, and performance degradation. Implement canary models, A/B testing, and cryptographic verification of model weights. Establish clear model governance processes with approval workflows for all model changes. Implement comprehensive security controls for training data throughout its entire lifecycle. Use data provenance tracking, integrity verification, and contamination detection to ensure training datasets remain trustworthy. Regularly audit data sources, labeling procedures, and data processing pipelines. Implement differential privacy techniques to protect sensitive information in training data. Establish secure development environments specifically designed for AI workloads. This includes container security, secrets management, code signing, and secure CI/CD pipelines for AI artifacts. Implement network segmentation, access controls, and monitoring specifically tailored for AI development activities. Implement robust input validation, output filtering, and behavioral controls for large language models and other AI systems. Use prompt templates, content filtering, response validation, and sandboxing to prevent prompt injection attacks. Monitor for attempts to extract system prompts or bypass safety controls. Use adversarial training, model distillation, ensemble methods, and other hardening techniques to improve model robustness against attacks. Implement multiple defensive layers that don't rely on a single protection mechanism. Regularly update defensive measures based on emerging attack techniques. Implement detailed logging of all AI system interactions, including input data, model responses, performance metrics, access patterns, and administrative actions. Use this telemetry for threat hunting, incident response, and forensic analysis. Ensure logs are tamper-proof and stored securely. Develop incident response procedures tailored to AI-specific attack scenarios, including model compromise, data poisoning, and adversarial attacks. Train response teams on AI attack techniques, forensic procedures for AI systems, and recovery strategies for compromised models and datasets. Conduct regular security assessments specifically focused on AI systems, including penetration testing, vulnerability assessments, and red team exercises that simulate real-world AI attacks. Use these assessments to identify vulnerabilities and validate defensive measures. Implement comprehensive governance frameworks that address AI security throughout the system lifecycle. Establish clear policies for AI development, deployment, and maintenance that incorporate security requirements. Include risk assessment procedures specifically designed for AI systems. Participate in AI security communities and threat intelligence sharing programs. Stay informed about emerging AI attack techniques, indicators of compromise, and defensive best practices. Contribute your own threat intelligence to help protect the broader AI community. Provide specialized training for AI developers, data scientists, and security professionals on AI-specific threats and defensive techniques. Ensure that everyone involved in AI systems understands their security responsibilities and can recognize potential attack indicators. Implement comprehensive security controls for AI APIs, including authentication, authorization, rate limiting, input validation, and output filtering. Monitor API usage patterns for signs of abuse or systematic probing. Use behavioral analysis to detect unusual usage patterns that might indicate attacks. Implement watermarking and fingerprinting techniques for proprietary AI models to enable detection of theft or unauthorized use. Use these techniques to track model distribution and identify compromised or stolen models in the wild. Incorporate adversarial training into model development processes to improve robustness against known attack techniques. Regularly test models against adversarial examples and update training procedures based on new attack methods. Implement secure deployment procedures for AI models, including runtime protection, sandboxing, and isolation. Use secure enclaves or trusted execution environments for sensitive AI workloads. Monitor model behavior in production for signs of compromise or manipulation. Implement comprehensive data privacy and protection controls, including encryption, access controls, data masking, and anonymization techniques. Use privacy-preserving machine learning techniques such as federated learning and differential privacy where appropriate. Establish comprehensive backup and recovery procedures specifically designed for AI assets, including models, datasets, and configuration data. Test recovery procedures regularly and ensure that backups are protected against the same threats that might compromise primary systems. Implement rigorous vendor risk management procedures for AI service providers, including security assessments, contractual security requirements, and ongoing monitoring. Ensure that third-party AI services meet your organization's security standards. Implement network security controls specifically designed for AI infrastructure, including network segmentation, traffic monitoring, and intrusion detection. Use VPNs, firewalls, and other security controls to protect AI communications. Implement continuous monitoring and alerting systems that can detect AI-specific threats in real time. Use automated response capabilities where appropriate and ensure that security teams are alerted to potential AI security incidents immediately. Establish procedures for regularly updating AI frameworks, libraries, and dependencies. Monitor for security vulnerabilities in AI software components and implement patches promptly. Maintain an inventory of all AI software components to facilitate rapid response to new vulnerabilities. Additional real-world insights. Let me share some additional real-world insights that demonstrate the sophistication of modern AI attacks and the importance of these countermeasures. The Morris 2 worm demonstrated how AI systems can be used to create self-propagating attacks that spread through AI infrastructure. This attack showed how traditional cybersecurity concepts like worms and viruses are evolving to target AI systems specifically. The attack on machine translation services showed how adversaries can manipulate AI systems to spread misinformation at scale by poisoning translation outputs. This has serious implications for global communication and information integrity. The virus total poisoning incident demonstrated how attackers can manipulate crowdsourced security platforms by submitting false information that corrupts AI-based threat detection systems. These real-world examples illustrate why traditional cybersecurity approaches are insufficient for protecting AI systems. The attacks we've discussed today target the fundamental characteristics that make AI systems valuable: their ability to learn, adapt, and make intelligent decisions. What makes AI attacks particularly dangerous is their potential for scalability and stealth. A single compromised model can affect millions of users, and attacks can remain undetected for long periods because they manipulate the AI's decision-making process rather than traditional system resources. The economic impact of AI attacks is also significant. The theft of proprietary AI models represents the loss of millions of dollars in research and development investment. The manipulation of AI systems can lead to incorrect business decisions, fraudulent transactions, and loss of customer trust. Consider the implications for different industries. In healthcare, compromised AI diagnostic systems could lead to misdiagnosis and patient harm. In financial services, manipulated fraud detection systems could enable large-scale financial crimes. In autonomous systems, compromised AI could lead to physical safety risks. The regulatory landscape is also evolving to address these challenges. Organizations must consider compliance requirements for AI systems, including data protection regulations, algorithmic accountability requirements, and sector-specific AI governance standards. Looking forward, we can expect AI attacks to become even more sophisticated as adversaries develop better understanding of AI systems and access to more powerful attack tools. The democratization of AI capabilities means that advanced attack techniques will become available to a broader range of threat actors. The defensive strategies we've discussed today represent current best practices, but they must be continuously evolved as new threats emerge. The security community must work together to share threat intelligence, develop new defensive techniques, and establish industry standards for AI security. One crucial aspect I want to emphasize is the importance of building security into AI systems from the beginning, rather than trying to add it as an afterthought. Security by design principles are even more critical for AI systems because of their complexity and the difficulty of detecting AI-specific attacks. Organizations must also consider the ethical implications of AI security measures. Some defensive techniques, such as output obfuscation or differential privacy, may reduce the utility or accuracy of AI systems. Balancing security and functionality requires careful consideration and ongoing evaluation. The human element remains crucial in AI security. While we can automate many defensive measures, human oversight and judgment are essential for detecting sophisticated attacks and making critical security decisions. This is why training and awareness programs are so important. Detection rules for AI attacks require specialized approaches that go beyond traditional signature-based detection. We need behavioral analysis that can identify subtle changes in model performance, statistical analysis that can detect data poisoning attempts, and anomaly detection specifically tuned for AI workloads. For prompt injection attacks, we need to monitor for unusual input patterns, attempts to extract system information, and responses that deviate from expected behavior. This requires understanding the normal operating parameters of your AI systems and establishing baselines for comparison. Model extraction attacks can be detected by monitoring for systematic querying patterns, unusual API usage, and attempts to probe model boundaries. Rate limiting and behavioral analysis are crucial for identifying these attacks before significant intellectual property is stolen. Supply chain attacks require monitoring of all external dependencies, verification of artifact integrity, and behavioral testing of all imported components. This includes scanning for malicious code embedded in model files and monitoring for unusual behavior during model loading and execution. Data poisoning attacks require continuous monitoring of training data quality, validation against known good datasets, and detection of unusual patterns in data sources. This is particularly challenging because poison data may be designed to appear legitimate to human reviewers. The detection rules we implement must be adaptive and learning-based because attackers are constantly evolving their techniques. Static signatures and rules will quickly become obsolete as adversaries develop new attack methods. Conclusion. Let me take a moment to summarize what we've covered today. The Mitre Atlas framework provides us with a comprehensive understanding of how adversaries target AI systems throughout the entire attack lifecycle. From initial reconnaissance through final impact, AI attacks require specialized knowledge and defensive approaches that go far beyond traditional cybersecurity. The real-world attack stories we've examined demonstrate that these threats are not theoretical. They're happening now, affecting real organizations and real people. The tape poisoning, the silence bypass, the supply chain attacks, the data exfiltration incidents. These are just the attacks we know about. Many more likely go undetected. The key insight I want you to take away is that AI security is not just about protecting the infrastructure that runs AI systems. It's about protecting the intelligence itself. The models, the data, the algorithms that make decisions. These are the crown jewels that adversaries are after, and they require specialized protection. The comprehensive countermeasures we've discussed provide a framework for protecting AI systems. But remember that security is not a one-time implementation. It's an ongoing process that must evolve with the threat landscape. I also want to emphasize the importance of community collaboration in AI security. The challenges we face are too complex for any single organization to solve alone. We must share threat intelligence, collaborate on defensive research, and work together to establish industry standards. The good news is that by understanding the adversarial playbook through frameworks like Mitre Atlas, we can build more resilient AI systems from the ground up. We can anticipate attack vectors, implement appropriate controls, and detect threats before they cause significant damage. Your role in defending AI systems is crucial. Whether you're a security professional, an AI developer, or a business leader making decisions about AI deployment. The techniques and countermeasures we've discussed today provide a solid foundation for building and maintaining secure AI systems. I encourage you to take these insights back to your organizations and begin implementing the security measures that are most relevant to your AI deployments. Start with a comprehensive assessment of your current AI security posture, identify the gaps, and develop a roadmap for improvement. Consider establishing an AI security center of excellence within your organization that brings together experts from cybersecurity, AI development, and business operations. This interdisciplinary approach is essential for addressing the complex challenges of AI security. Also, don't forget the importance of testing your defenses. The attack scenarios we've discussed today can be adapted for red team exercises and security assessments. Regular testing is essential for validating that your defensive measures work as intended. The threat landscape will continue to evolve and new attack techniques will emerge. Stay engaged with the security community, participate in threat intelligence sharing programs, and continuously update your defensive strategies based on new threats and lessons learned. Remember that AI security is ultimately about enabling the safe and beneficial use of artificial intelligence. By implementing robust security measures, we can build trust in AI systems and ensure that they continue to provide value while minimizing risks. The future of AI security depends on our collective understanding of these threats and our commitment to implementing robust defenses. By working together and sharing knowledge, we can stay ahead of the adversaries and ensure that AI continues to be a force for good in our organizations and society. As we conclude today's training, I want to remind you that the knowledge you've gained here is just the beginning. The field of AI security is rapidly evolving, and continuous learning is essential. I encourage you to explore the Mitre Atlas framework in more detail, participate in AI security communities, and contribute to the collective knowledge that will help protect AI systems worldwide. The 20 real-world attack stories we've examined today represent just a fraction of the threats facing AI systems. Each of these incidents provides valuable lessons about the creativity and persistence of adversaries, as well as the importance of implementing comprehensive defensive measures. What makes these attacks particularly concerning is their potential for widespread impact. Unlike traditional cyber attacks that might affect individual systems or networks, AI attacks can manipulate the decision-making processes that affect millions of users across multiple organizations. The sophistication of these attacks also continues to increase. We're seeing adversaries who understand machine learning theory, have access to powerful computational resources, and can develop highly targeted attacks against specific AI architectures and deployment patterns. This is why the defensive approach we've outlined today is so important. It's not enough to simply apply traditional cybersecurity controls to AI systems. We need specialized defenses that understand the unique characteristics of AI workloads and can detect and prevent AI-specific attack techniques. The countermeasures we've discussed represent a comprehensive approach to AI security that addresses the entire attack lifecycle. From preventing initial reconnaissance to detecting and responding to successful compromises, these controls provide multiple layers of defense against sophisticated adversaries. But implementing these controls is just the first step. The real challenge lies in maintaining and evolving these defenses as the threat landscape continues to change. This requires ongoing investment in AI security capabilities, continuous learning about new attack techniques, and regular testing and validation of defensive measures. I want to emphasize again the critical importance of the human element in AI security. While we can automate many aspects of defense, human expertise and judgment remain essential for understanding the context of threats, making critical security decisions, and adapting to new attack scenarios. The training and awareness programs we've discussed are particularly important because AI security requires knowledge that spans multiple disciplines. Security professionals need to understand AI concepts. AI developers need to understand security principles. And business leaders need to understand the risks and implications of AI deployment. Thank you for your attention today, and I hope this comprehensive training has provided you with valuable insights into defending against the evolving threat landscape targeting artificial intelligence systems. The real-world attack stories we've examined and the countermeasures we've discussed will serve you well as you